Hi, this is 6.7 financial modeling, and basically one of the easier sections of this chapter, at least, um, because it just requires a couple of formulas. The first one is compound interest, and it's A equals P times 1 plus R over N raised to the NT power. And basically, compound interest, as we discussed in class, is about interest gained on interest. So it's unlike simple interest, where you just get a certain amount of interest rate for a certain block of time, and then you pull the money. Well, this one actually gains interest, put the money back in, and it gains interest again, not only on the original principal, but on the principal, the interest that you've already gained on the first time it came up due. And so that's kind of what compound interest is. So the P stands for the principal, the rate stands for the R stands for the rate, and it's written as a decimal. So if it says 6% interest rate, it's 0.06. So the number of times compounded yearly. So if they told you it's compounded monthly, then of course N would be 12. If it says it's compounded quarterly, which in a lot of cases that's what it is, it's N equals 4. If it says compounded semi-annually, of course N would be 2. T is the number of years, which is the time, and A is the amount at the end of the period. And recall that A has to be bigger than P because you want more money when you pull the money out than what you put in. Otherwise, you're losing money. It's not like the stock market. So continuous interest, A equals P times E raised to the RT power. So now the difference between continuous and compound interest, continuous is there's no elapsement of time before it's compounded. So if it's being compounded, let's say monthly, 30 days have to go by before it's compounded again. If it's compounded semi-annually, then 6 months have to go by before it's compounded. This one is continually getting compounded. Okay, there's no time that goes by. And P is the principal, R is the rate. Again, it's a decimal. T is the number of years or the time. A is the amount at the end of the period, and again, A has to be bigger than P. So these are just a couple of formulas that you have to know in order to do the problems. And I gave about 3 examples here. First 2, okay, is based on the first formula, and the last one's based on the last formula. So, but example 1 says the amount resulting from $10,000 invested at 6% compounded monthly for 20 years. So what they want to know is how much is at the end of the period. So you put $10,000 in the bank or whatever, you invest at 6% compounded monthly. So it looks kind of like this. So A equals P times 1 plus R over N to the NT power. So you want to know what the amount at the end of the period is. So you just matter putting the numbers in the right place. So $10,000, okay, times 1 plus the rate, and the rate is 6%, so it's 0.06, divided by N, which is the number of times it's compounded per year, and it's compounded monthly. So N, of course, would be 12. And then that's raised to the N times T power. Now, NT, the product of T, is basically how many times it's being compounded all together. So if N is 12 and T is 20 years, it's going to be 12 times 20. And I believe that's 240 because it's the product of 12 times 20, so it's 240 times. Now, back in the old days, before the calculators became really super nice, we would actually calculate 0.06 divided by 12 in an intermittent step, and then put that number in here, okay, and then raise it to the y-axis, kid 10,000, and then multiply that by 10,000. But with the new fangled calculators nowadays, you can actually just plug this in the way it appears. So you just get 10,000 left parentheses 1 plus 0.06 divided by 12 all over and then raised to the 240th power. So those 2-line calculators are super nice these days, and wish I had that when I was a student. So we got 10,000, 1 plus 0.06 divided by 12, and raise that to the 240th power. And you have, wow, quite a bit of money. You have $33,102, and we're going down to the nearest penny, so it's going to be 4 cents. So you've more than tripled your money. I mean, You put in $10,000 and you got $33,102.04. Now, I would suggest when you're doing this on a calculator, these things, well, not this one, this is a graphing calculator, you're not allowed to use these. But when you're doing this, okay, make sure you at least double check your calculations. I have a lot of people who put this down and they mispunch a number. They might hit a 5 instead of a 6 when they hit 0.06. And of course, that number's going to go down. And your theory is right. You just mispunched the button on the calculator. So I would really encourage you to double check it, the, the buttons that you push. So, okay. Now that's example one. Now example two is asking for us to, how long will it take for $1,000 to double? Which means you want to know how long it takes for $1,000 to get to $2,000 at 4% compounded quarterly. So this time we already know what we start with. We know how much we're going to end up with. We want to know how long it takes to get for that to happen. So you still begin with the same formula, A equals P times 1 plus R over N to the NT power. So it's going to be $2,000 because you want your money to double from $1,000. And notice 2,000 is more than 1,000. So if you ever end up with a number over here smaller than this number in this section in financial modeling, you got some problems. So, and then 1 plus the rate, which is 0.04, over the N power is compounded quarterly. So that's 4. And then raised to the 4 times T power. T is the time. So now, first thing I notice, I can do a little bit of this mentally. You know, I can divide by 1,000 over to the other side. And the reason you want to divide by 1,000, you want to go to the path of least resistance. I mean, if the 1,000's over here, you got less to deal with over here. So if I divide both sides by 1,000, you get 2 equals 1.01. Now that one I'm going to go ahead and do a little bit of mental math because 0.04 divided by 4 is obviously 0.01. And then raise that to the 4t power. And if you remember back in 6.6, when we had those logs on one, the exponentials on one side and numbers on the other side, there's a way to do that. You take the natural log of both sides. So you take the natural log of 2 equals the natural log of 1.01 raised that to the 4t power. And the reason you do that is so you can use the power rule for the 4t. You can bring the 4t down. So this becomes the natural log of 2 equals 4 times t times the natural log of 1.01. And since you're trying to solve for t, you're trying to figure out how long that is. The 4, if it's over to the other side, and the natural log of 1.01 is to the other side, you've isolated the t. So then it becomes just a matter of what is the natural log of 2 divided by the 4 times the natural log of 1.01. Now, when you're putting this onto a calculator, be very careful. This 4 is down here with this. So you probably wouldn't want to put parentheses around it just to reinforce that that's what you're going to do. Because you do the natural log of 2 divided by 4 times the natural log of 1.01 without these parentheses. What it's going to do is this. It's going to take the natural log of 2 divided by 4. And it's going to multiply that by the natural log of 1.01. So the parentheses around that group down there forces the natural log of 1.01 to stay down in the denominator. So it's a very common mistake that students make. So, all right, so let's see what we have. We have natural log of 2 divided by, now my parentheses, 4 times the natural log of 1.01, close my parentheses off, and I have 17.4 approximately, 17.42 if you want to get a little closer, years. So with this situation, okay, it really wouldn't matter what the number was right here, if it was $1,000 or whatever, because if you had $10,000, it's going to grow to $20,000, but it'll take the same amount of time. So the number I put here was didn't really matter. You want your money to double. So when you divide, if you have 1,000 here, this would be a 2,000. But if this was 20,000, this would have to be 40,000. But when you divide it by the 20,000, you end up with that 2 anyway. So this is a good little example to show you guys, if you have kids and you want your kids to have, a certain amount of money in this certain situation. So if you're going to send them off to college, at this, 4% rate, and it's almost 17 years, so it's almost an 18-year-old kid. Okay, so when they're born, you have to, if you think $100,000 is sufficient to send a kid through school, then you better be willing to dish out $50,000 at that point. So because then $50,000 would grow to $100,000 in this amount of time. So it's a nice way to figure out when your finances down the road under certain situations. So this is assuming that you never pull the money out of the bank, assuming the interest rates never change on you, which they do, but it gives you a good idea at least. So in example 3, how much money does Jack need to invest to have $80,000 in 5 years? So he needs $80,000 in 5 years. How much should he put in the bank now? How much does he need now? When you 10% compounded continuously. So this one is A equals P times E raised to the RT power. So he needs 80,000 P, and in E, the rate is 10%, so it's 0.10, and then times the time, and that is 5 years. So that becomes 80,000 equals P times E to the 0.5. 0.1 times 5 is 0.5. Now this one probably will not take as long. I'll tell you why. It's not that it's continuous, which does make a little bit of a difference, but the big difference is the interest rate. The interest rate compared to this is 10% compared to 4% on the previous problem. So this one, I would not be surprised it would take, if it takes only 5 years to do this. So probably, you think, well, maybe it's $70,000. It might be, but I think it might be even less than that. So let's find out. So what I'm going to do is divide by the E to the 0.5 to the other side. So we have 80,000 divided by, okay, shift LN, so it's E to the power of 0.5. It's $48,522.45. So $48,522 and some odd pennies will grow to $80,000 in 5 years. Okay, well, $48,000 is a lot of money too. Yeah, but that's 80, almost doubles, not quite doubles, but it's only took a 5-year span to do that. Why? Because the interest rate is so high there. Plus, it's doing a continuous rate on top of that. So, but anyway, this is 6.7 financial modeling, and it's basically driven by these two formulas for the most part. And problems, they're pretty much on the same difficulty level as what I'm showing you here. It shouldn't be much more difficult than these three. So that's it.